My name is Yiyang Chang. It's a pleasure to be here to talk about our recent work on network validation. So in this talk, I will basically talk about how we can validate network designs under uncertain demands and failures. So this is joint work with my professor, my advisor, Professor Sanjay, and Professor Mohit Tawarmalani at Purdue. So as we all know today, network design today is an ad hoc process, and validating design normally comes as an afterthought. And this fact is actually a sharp contrast to the status quo in chip and software industry, where the verification tools is a $10 billion business. So motivated by that, a lot of work has been done on network verification, which is mainly focusing on ensuring the correctness of network data plane. But we would like to think this problem from a fresh and more broader perspective. So we want to validate network designs quantitatively. So our goal is to have an approach which is formal and that can guarantee network performance, such as bandwidth or link utilization, under different failures and traffic scenarios. And we want to later use this formal approach to guide us to inform the network design problems. So why is network validation problem is hard? The first reason is because the scenarios of interest are too many to verify. So for example, if you're trying to validate failure problems, the number of scenarios that you have to validate are normally exponential to the number of failures. And for another example, if you're trying to validate all possible traffic demands in the network, the scenarios are not even enumerable because the traffic demand, as we know, is a continuous variable. So the second reason this is a hard problem is because network adaptation. And this network adaptation normally makes the problem intractable. So what do we mean by network adaptation? So if you can look at this graph, we know that networks today are flexible and agile, and it can adapt to changes happen in the network, such as demand shifts or failures. And the network can adapt to them by rerouting or throttling the traffic and to achieve a better performance. And this is more and more common today in the network because the emergence of SDNs and NFVs. So there are some existing tools to bound worst-case performance for a network, but they have some limitations. So they either assume the networks do not adapt, or consider limited types of adaptations of the network to make their problem tractable. So our work is a general framework for network validation problems. So it can find the worst-case performance for the network across all the failure scenarios you're interested in, and at the same time assuming the network can react in the best fashion for each of these scenarios. So if you look at the graph to the right, so assuming we have a lot of scenarios possible, and for each of them, the network can adapt in its best fashion. It could be rerouting, it could be throttling traffic, and for each adaptation, you end up with a metric. And and across all possible scenarios, as is shown from 1 to n here, the max of these metrics will be the worst performance. And be careful here, the performance here has the priority that the less the better. So considering this network adaptation normally results in intractable problems, and we have to handle that drawing on cutting-edge optimization technique. So this framework not only solves network validation problems, it can also apply to network synthesis, and as I will talk in the end of this talk. So let me give you a concrete example on what a network validation problem is. So assume we are trying to validate the network property under failures. So as you can see here, there are 3 key components to a network validation problem. They are uncertainty set, adaptations, and performance metric. So in this example, the uncertainty set would be the set of the scenarios you care about, and here we can choose to be F or fewer link failures. And the adaptation means the way you constrain your routing, and here we can choose to be flexible rerouting, and we use something called multi-commodity flow. And the performance metric here is the thing you validate on, and here we choose that to be utilization of most congested link. So to summarize the problem we solve in one sentence, given up to f links may simultaneously fail, what is the worst case performance across any link, across any failure scenarios? Okay, now let's take a closer look to the formal formulation of this problem. Now there will be a little bit math, but don't worry too much about it. So if you remember that we just mentioned there are three key components: uncertainty set, adaptations, and performance metric, and they map each to a part of this formulation. So the interesting thing for this formulation is it's two-level. So the inner problem, which is the main problem, it actually assumes a fixed scenario, and for each scenario it computes the best fashion. It computes the best way it can adapt to this scenario. And the inner problem is normally easy to compute because it needs to finish online, and it's normally a linear program. For example, in the example we just mentioned, for example, multi-commodity flow is such an inner problem. So the outer problem instead is normally hard because it needs to explore over all the possible scenarios in the uncertainty set. So and after exploring all of them, it can give the worst case performance. So our framework has a great applicability. We can not only model the F or fewer link failures, we can model other failure models such as shared risk link group. We can also model validated failures. We can also validate demands. And by adaptations, you can choose more than MCF. You can also do rerouting constrained by tunnels. For performance metric, you can also choose more than utilization. You can also choose such as bandwidth. So before we really solve the problem, we have to do one more thing. So we need to reformulate this problem as we just saw, which is normally called a two-stage problem, two-stage formulation. So we want to transform that to one stage. And the technique we use here, which I won't elaborate, is a standard technique in optimization, which is called LP dualization. So if we apply this technique onto the example we just saw on failure validation, this is the final formulation we have. So don't worry too much about the details in this formulation. Just focus on, there are some interesting facts I would like to share with you. So first, if you look at on this constraint, this xf belongs to x. So it actually depends on the failure model you choose. So for example, we just said we want to do simultaneous f-link failures, and this constraint can be simply replaced by summation xij equals to f. And the next thing is this model itself, this formulation itself can be converted to a mixed integer linear program. And in general, the validation problem can be nonlinear. So I just show you some scary equations, scary formulations, and we know that they are all intractable problems. But how can we solve them? We know these intractable problems are normally hard to solve to optimality, so we decide to only focus on upper bounds, which is basically a relaxation approach. And we argue that the upper bounds are sufficient for validation use because it only gives you a conservative answer. And if you rely on a conservative solution, you won't get incorrect. So the goal here is to develop a general approach which is applicable to many different validation problems, but still we can use that we can still leverage some problem-specific structure. And to handle the intractability, we have to leverage cutting-edge techniques from nonlinear optimization community, which is called ROT relaxations. So it is a general approach to relax non-convex problems into tractable linear programs. It's a family of relaxations, and it has different levels of hierarchy. So you can do higher levels of hierarchy of relaxation, and you will get closer to the optimality. But in the same time, you pay the price of incurring higher complexity. So for scalability reason, this work only focuses on the first level, ROT relaxation. So let me show you a quick example how ROT relaxation works. So given this optimization problem, it's nonlinear because there is a nonlinear term xy in the objective. So how we can relax it? So the first step is we take each of these two constraints and multiply them together and end up with this. So apparently we have a nonlinear term xy here. So we simply replace it by a new variable z. And as we can see there in the objective, the xy was there too. Then we'll do the same thing. So by doing this simple mechanism, we eliminate the nonlinearity in the formulation and end up with a linear program. So if we solve the relaxed formulation again, it will give you an upper bound. So for this example itself, both the original formulation and the relaxed formulation gives you the same result. But in general, it could be different. It's a relaxation anyway, right? So we have some interesting results on the effectiveness of RLT. So we compare the results with two theoretical benchmarks, and which are called oblivious routing and affine adaptations. So don't worry about the details of the name too much. So more details are put in the paper. So the bottom line of these two benchmarks are both of them bound worst-case performance across failures and demands, but they have limited network adaptations. And our results show that the first level RLT relaxation actually dominated the result of both oblivious and affine adaptations. And even better results are possible if you can exploit some problem-specific structure combined with RLT. So we evaluate our framework. We evaluate our failure validation problems with real topologies drawn from Internet topology too. We also evaluate with real and synthetic traffic matrices like Abilene 6 months traces, or synthetic approach like using gravity model. So the first result I would like to show is what's the effectiveness of our RLT. So we compare maximum link utilization, also called MLU, between the optimal IP scheme versus our RLT relaxation LP. So if you look at this graph, the y-axis is the maximum link utilization. The x-axis is a 24-hour time span. And for each 5 minutes, we have a traffic matrix from Abilene. And for each of the traffic matrix, we compute the maximum link utilization. So the curve you see here is a bottom line, is a baseline. So it shows the MLU for no failures. So now I show you a green curve, which is the MLU computed using optimal IP under 3 failures. So as you may notice there are some region which has MLU larger than 1. That means the network cannot handle all possible 3 failures under those traffic matrices. So next, I will show you the result of our RLT results. And as you can see that, surprisingly, they exactly match. So that means actually RLT matches optimal results in these experiments. And we repeated the experiments with different topologies and different traffic matrices, and the result is the same. So moving on, we compare our result with another system called R3. So R3 is a paper first published on SICOM 10. And it can determine the MLU if MLU is less than 1 under F failures, but it only gives a valid bound when MLU is less than 1. So if you look at this curve, this orange curve shown, this is the result we get by R3. And there are some gaps in the curve, as you can see. And those gaps are exactly where MLU is larger than 1, because R3 doesn't give a valid bound there. But for the region where MLU is less than 1, you can see that our framework can get a tighter bounds than R3. So the result shows that the first level RLT actually dominates R3 results whenever R3 provides a valid bound. And there are some other advantages to our approach, like, for example, it can detect bad failures. It can generalize to other validation problems. So the next result I would like to show is how we can use framework to detect bad failures. So the framework allows us to find failures which impact the network the most. And the random search approach doesn't work here because it's not efficient. So for example, for a given traffic matrix in Abilene, only 0.5% of the 3 failures are bad. So, but our framework can identify that. So we emulate these found bad failures on an SDN testbed and to understand the latency behavior. So as you can see here in the graph, there are 2 groups of curves. The black group is the bad failure scenarios, which are identified by our framework. And the red ones are randomly picked up by from all the possible 3 failure scenarios. And as you can see here, the bad failure scenarios really has a large latency. And that actually shows it impacts the performance of the applications which care about latencies. So the third result I would like to share with you is the running time. So we compare the running time between the relaxation LP and optimal IP. So we do this on a scaled Yiyang network which has 32 nodes and 1,000 edges under 3 link failures. So the result shows that ROT is actually very quick. It finished in 600 seconds, where IP for those who finish in 2 hours, the average is about 3,800 seconds, and there even 40% of them didn't finish. So if you go to a higher number of link failures, the relaxation LP doesn't degrade too much, but the IP runtime just explodes. So far we have talked about one example about failure validation. Now let me quickly walk you through a tunnel selection validation example. So the problem can be summarized as, for a given choice of tunnels, are utilizations of all links across traffic demands within acceptable limits. So here are some partial results. More results are in the paper, so please feel free to read that. So if we model the demand in predict demand model, which means each demand in the network can be expressed by weighted averages of historical matrices. If we assume that the validation problem is a linear program, and on Abilene network, we find that the first level ROT relaxation actually matches the optimal. And when we evaluate on different models, different tunnel selection strategies, we actually find some widely used tunnel selection heuristics sometimes perform poorly. For example, k-shortest path or shortest disjoint heuristics. And we have a more robust tunnel selection heuristic in the paper, which actually performs much better. So now let me come to the last part of the talk, which is how we can use the validation to inform network synthesis. So I will use a concrete example to explain this, and this example is optimal capacity augmentation. So it incrementally adds capacity to the existing links, but we want to minimize the cost of adding these capacities. And the target here is to make sure the augmented network can handle all the failure scenarios. So one can use the framework we proposed for synthesis in 2 ways. First, you can just run one single LP, but you can only get a conservative solution, which is an upper bound. For another one, you can do an iterative approach, which gives a lower bound on cost at each iteration. So I will focus on the second one for the time constraints. So if you look at this graph, this is Abilene topology. And the steps is like this. So we first validate if the MOU is less than 1. And if it is already less than 1, we're done, because the network is already able to tolerate all failures. But if it is bigger than 1, as you can see here, this links in the red are the worst case failures. So we throw that into an augmentation linear program, and it will tell you where to augment, which is the link 110 shown in the green. So then we iterate it back and find the next counterexamples, then iterate until we're going on, until the MOU reaches to 1.0, which means the network so far has already has the capability to handle all the 3 failures scenarios. And the links in green shown are the links where it needs to be augmented. So to conclude, this work is an early effort on formally verifying quantitative network properties under uncertainty. And it's a generic framework for a wide class of network validation problems. It also considers network adaptations, which results in intractable problems, and we use IoT to handle that. So the results are promising. We get tighter bounds than existing approaches. And in some cases, we even get exact results to the optimal. And last but not least, the validation framework can also enable a network synthesis problem in the future. So with that, I would like to take questions. Thank you.
Marco Francaust. So I have a quick question. This is very interesting work. I appreciate the elegancy of the framework itself. Now, I was thinking about the validation problem and whether there is any underlying limitations regarding what you assume the validation problem to be. Is it correct to say that the validation currently is assumed to be an LP in your framework? Sorry, the adaptation problem.
Okay, is the question that we assume validation problem to be a linear program?
The adaptation problem, is it assumed to be an LP?
Sorry, the
adaptation
problem.
Yeah.
Okay, so if you remember, I mentioned that there's an inner program. So there's an inner formulation. The inner problem needs to be actually convex. So LP is a normal form. So as long as it's a convex problem, this framework can work.
Okay. So I wonder if you have put any thought. So these days we have software-defined networks and NFV, and so much of these adaptations that happen are regulated by controllers which could potentially run arbitrary code and decide, how they're going to make adaptations in face of various type of events, like Panda was saying before. I wonder if you have thought, how you will be able to monitor or understand the behavior of arbitrary controllers and understand if they are essentially fitting in the category of convex adaptation problems or not, so that one could potentially use your tool with complex networks.
Okay, let me understand your question. So even under SDN, which can be complex, does this framework fit to under some complex network context? Is that?
Yeah, you
fair?
can summarize.
Okay. So this framework doesn't. I mean, the complexity of network. It could be very complex, but the basic assumption of this framework is you have the ability to model the complexity, whatever complexity you have, in the convex in the convex formulation we just mentioned. So if you have the ability, if you can model your network behavior in that convex problem, then this framework should help.
Okay, thank you.
Thanks.
Great. Any other questions? Okay, let's thank our speaker.